In this lecture video, we are continuing Chapter 17, Section 6, looking at practice exercise 9. So we're given a KSP value for manganese 2 hydroxide, and we're asked to calculate the molar solubility of manganese 2 hydroxide in both pure water and in solution that contains 0.020 molar NaOH. In the previous video, we discussed the fact that we expect the molar solubility to be larger in pure water than in NaOH because of the common ion effect. So let's go ahead and calculate that and see if we're correct. So for part A, in pure water, so again, the first thing for any KSP problem, write your KSP reaction. I know that means I have to start with my solid dissolving into ions. I know I've got 2 hydroxide ions because I've memorized hydroxide as a -1. Therefore, I've got manganese that is a 2+ ion. My KSP expression is going to be manganese 2+ times hydroxide squared, ICEQ with molarity. Solids we ignore. We always start, because we're not told that we have any products with 0, but they're going to form this 1 to 2 mole ratio, which we keep at equilibrium. Now we have to stop and think, how do I solve for x? I'm given the numerical value of KSP. So I can say KSP, we're told, is 1.6 times 10 to the negative 13th equals products over reactants. So x times 2x squared. The reactants are solids, so they are not included. And I just realized this is a negative 13. It's given there. So now I can solve for x, 1.6 times 10 to the negative 13. X, 2x squared is 4x squared. 1.6 times 10 to the negative 13. My goodness. 13 equals 4x cubed. So I solve for x, 1.6 times 10 to the negative 13 divided by 4 to the 1/3 power. So now on the calculator, we go ahead and plug in 1.6 second e negative 13 divided by 4, enter, caret, parentheses, 1/3 close. Enter, and I got 3.4 times 10 to the negative 5th. Units will be molarity, and I see that x stands for my manganese. And then I can use my mole ratio to be super thorough for 1 mole of manganese 2+ for every 1 mole of manganese 2 hydroxide. Because it's important to remember when we're solving these problems, we have to convert with the mole ratio to get the entire chemical formula, not just one of the ions, because sometimes it won't be a 1-to-1 mole ratio. So that tells me the molarity in pure water is 3.4 times 10 to the negative 5th. Let's go ahead and look at part B if it's in NaOH. So in part B, I know my KSP value and my expression, remember, because we wrote the reaction down in A, Mn 2+ times OH minus squared. So looking at what we're given KSP, and in part B, I know my molarity of hydroxide is 0.02. So then we can just solve for the manganese. We do not need to use an icebox for this problem. So rearranging, I know that Mn2+ equals KSP divided by OH minus squared. So my KSP value, 1.6 times 10 to the negative 13th, divided by 0.020 squared. The reason I'm doing this is because we're told the solution already contains 0.02 molar hydroxide, so that number goes here. You might be asking, but what about the hydroxide that comes from the compound being dissolved? Well, because of Le Chatelier's principle, common ion effect, equilibrium shifts left, not much is going to come from that solid. And also, even if we think about it, 2x, if it was still dissolving as much as it could, that molarity of hydroxide is just 3.4 times 10 to the negative fifth, which even times 2 is significantly smaller than this number, so we can ignore it. So to finish this up, I can then solve for the Mn2 plus molarity, which is the same as my MnOH2 molarity because it's a 1-to-1 mole ratio. And that equals 4 times 10 to the negative 10th molar MnOH2. So let's go ahead and compare this. We said we expect the compound to be more soluble in water than in the NaOH solution, and it is. So this is a much larger number than this. So that follows what we were expecting to see. Another factor affecting solubility is pH. So I know that H plus reacts with hydroxide to make water. So if you have a compound that has a basic anion like we see here, the compound will be more soluble in acidic solution. Because what's happening? I have my magnesium hydroxide, I add acid to it, and I'm going to form water between the H plus and the OH minus, which then leaves the magnesium 2 plus as dissolved. So what we're looking at in this slide here, I have my solid magnesium hydroxide that's insoluble in water, but if I add acid and stir, I can make that compound dissolve. So if we have a compound with a basic anion, it will be more soluble in acidic solution. And let's look at some examples on the next practice exercise. So practice exercise 10. For the following slightly soluble salts, meaning in general they're not soluble in water, write the net ionic equation, if any, for the reaction with acid. So what we need to remember any ionic compound with a basic anion will be more soluble in an acidic solution. So this we need to remember our topics from chapter 16. So remember which I know anions are either neutral or basic. Neutral anions, the conjugate base of a strong acid, chloride, bromide, iodide, nitrate, perchlorate. We don't talk about sulfuric acid because the conjugate base is actually acidic because it's a diprotic acid. So all of these anions are neutral, so all other anions for the most part are going to be considered basic. So looking here, I can see my anion is sulfide. This is Mn2 plus. Sulfide is not basic, so it will be more soluble in acid. Net ionic equation, so I'm looking at just adding H plus. Go in the forward direction because H plus is strong, and I'll make H2S, right? I have to make a neutral compound, so I'll balance that. And I'm left with Mn2 plus aqueous. So that shows me that if I had manganese 2 sulfide, it would be insoluble in water, but I could add acid and have that compound dissolve. Let's look at PbF2. So I know I've got my fluoride anion, I've got my lead 2 plus cation. Fluoride is indeed basic because it's not one of my neutral anions. That means when I add acid, reacts in the forward direction to make HF, right? 1-to-1 ratio. So the conjugate acid of F minus, and Pb2 plus. And lastly, we could balance it because I've got 2 fluorides on the left, so I need a 2 over here and a 2 there. And lastly, gold 3 chloride. Now my anion is chloride, cation is gold 3 plus. If I add acid, I'm going to see no reaction. And that's because chloride is the conjugate base of a strong acid, so it's not basic. It's not basic, so it's not going to be attracted to H+. There will not be an attraction here. No reaction will occur, so the gold 3 chloride will not be more soluble in acidic solution. So again, the key here to figure out will a salt dissolve in acid, you need to look at the cation, look at the anion, and identify is the anion basic. If it is, the reaction will occur. The compound will be more soluble.